Hey guys, welcome to chapter 7. So in chapter 7, we're going to start doing some chemical reactions. So what have we done thus far in this class? We've explored subatomic particles, protons, neutrons, electrons. We've put atoms and elements together to form compounds, so ionic compounds, covalent compounds. We saw how electrons dictate all of that. So now what we're going to start doing is we're going to do chemical equations or reactions. So we're going to take two compounds, we're going to put them together, magical chemistry is going to happen, and we're going to get a result on the other side. So that's the chemical reaction piece of this. Then, once we look at that, we can then talk about mathing with some of these compounds. So we'll come back to the idea of dimensional analysis, unit conversions, but we'll do it from a chemistry standpoint, a chemistry framework. So that's what we're going to do in chapter 7. This particular lecture is just going to focus on chemical reactions, so symbolically representing them and then balancing them. So in chemistry, we symbolically represent everything. So what we're going to look at today is how do we symbolically represent chemical reactions? Here are two ways that we can symbolically represent a chemical reaction. Both of them are symbolically representing the same reaction. So on the top, we see numbers and letters. So this is the way that we're going to talk mostly about how we depict chemical equations. But this is also a way that we can depict it with pictures of atoms and compounds, okay? So the way that we read this here's our reaction arrow. Let's look at that first. So this arrow is our reaction arrow. That's essentially our equal sign in chemistry. Everything on the left of the reaction arrow is what we call the reactant. What are we reacting or mixing or adding together? So here's our reactants. Everything on the right-hand side of the reaction arrow is our products. What are we producing? Okay. This one happens to have two reactants and one product. But there is no rhyme or reason to how many of each. We could have one reactant and 3 products. We could have 5 reactants and 2 products. We could have 10 reactants and 1 product. So it doesn't really matter how many are on each side. Just know that these are reactants, these are products. Okay? The other thing we see here are numbers. So we see big numbers in front, little numbers underneath. Let's talk first about the little numbers because we've seen those before. These little numbers are called subscripts, and they tell us about identities, so the identity of this compound. So this is H2. So what that tells me, there's 2 hydrogen atoms that are bound together. And that's what we see here. One dot is one hydrogen, the other dot is the other hydrogen. They're bound together. Here we see O2. So subscript 2 tells me there's 2 oxygens bound together. 1, 2. And then here we see a 2 for hydrogen. So again, 2 hydrogens, 1 oxygen. Excuse me. 2 hydrogens, 1 oxygen. So it tells us about the identity. When we are balancing these equations, you may not touch subscripts, period. They are off limits. Don't touch them. What we see in the front here is a big number. This big number is called a coefficient. A coefficient tells us about quantity, coefficient, quantity. So here I see a coefficient of 2 in front of this hydrogen, and that tells me that there are 2 of these compounds present. 1, 2. There is a coefficient here. The coefficient is 1. So remember that the number 1 in chemistry is often implied. If it makes sense in your brain to write a number 1 there, by all means, write the number 1 there. But it's an implied coefficient of 1, so just one molecule. And then we see it again here. So here's 2 molecules of water. So it tells me the quantity, and we see 1 and we see 2. When we are balancing chemical equations, we can change the coefficient. That's the only thing we can change, is that big number out front. Okay. So again, reactants on the left, products on the right. Another thing that you may see very often written with these chemical equations are these letters after each of the compounds. So these letters just tell us what state each of these are in. So if you see a G, just like this one has a G for all of them, if you see a G written after it, that tells us that it's in the gas state. If there's an L, it's liquid, S, solid. This AQ, you'll see that one very often. The AQ means it's an aqueous solution. So what AQ means is that it's dissolved in water. So you may see something like this, where you got NaCl, and then there's an AQ after it. And what that means is that that NaCl is dissolved in water. So that's what that aqueous means. It just is dissolved in water. All right, so balancing chemical equations. The law that's going to govern us here is it's actually the first law of thermochemistry. It says matter is neither created nor destroyed during a chemical reaction. An application for us that might be helpful is atoms are neither created nor destroyed during a chemical reaction. So when we are looking at chemical equations, it's going to be our job as chemists to predict, well, how many of each particle do we need to react together, and how many of each particle is produced during this chemical reaction. And how do we know how many of each? Well, it's got to be balanced, okay? So there is no shortcut to this. There is no faster way to do it. The way that I'm going to teach you is the way that I still balance equations myself. It's tedious, it's kind of long, but it works. And it's the only way that works all the time. All right, so what we're going to do is we're looking at this chemical equation. This is not a balanced chemical equation. So the first thing I'm going to do is I'm just going to take inventory of what I have on each side. So I see that on the reactant side, I've got some carbon atoms, I've got some hydrogen atoms, and I've got some oxygen atoms. And I'm going to go through and I'm going to tally how many of each I have. So I've got 1 carbon atom over here. I've got 4 hydrogen atoms. And I've got 2 oxygen atoms. And then I'm going to do the same thing on the product side, just to see if anything matches or doesn't match so that we can change the quantities. Just a helpful hint here. On the reactant side, I wrote carbon, hydrogen, oxygen. Just for ease, you should probably write carbon, hydrogen, oxygen on this side too, because you're going to bounce back and forth, and it'll just be easier if they're right across from each other. All right, so looking at carbon on the product side, I've got 1 atom of carbon. Looking at hydrogen, I've got 2 atoms of hydrogen. And looking at oxygen, be careful here. So I see oxygen is actually in 2 different compounds. So I've got 2 atoms of oxygen from carbon dioxide, so 2. And then I've got 1 atom of oxygen from water over here. So plus 1, which gives me a total of 3. Okay. If this were a balanced chemical equation, these numbers should be the same on both sides. So 1 and 1. Oh, the carbons are balanced, so nothing we need to do there. Hydrogen, 4 and 2. Well, that can't work. We can't start with 4 hydrogen atoms and then poof, 2 of them disappear. That's not how chemistry works. So when we produce hydrogen, we must produce 4 atoms of hydrogen. So what can we do that would give us 4 atoms of hydrogen? Well, my guess is that it's not just 1 molecule of water that gets formed. My guess is that we actually form 2 molecules of water. Okay? So if I form 2 molecules of water, well, how many total hydrogen atoms would that be? We take coefficient times subscript. So 2 times 2, that means 4 atoms of hydrogen were formed. Okay? So that balances our hydrogens. Great. What does that also affect? Yeah, it affects the oxygen, right? So if 2 water molecules are formed, we've also got 2 oxygen atoms here. So again, coefficient times subscript, so 2 times 1. This isn't 1 anymore. This is now 2. And 2 plus 2 is 4. Okay. Carbons, balanced. Hydrogens, balanced. Oxygens, I have 2 on this side, and I have 4 on this side. Well, that can't happen. We can't start with 2 and then poof, 2 more pop out of thin air, okay? So what does that mean about our reactant side? Yeah, it probably means that we need 2 molecules of oxygen in order for this reaction to take place. Okay, so if I change that coefficient to a 2, I take coefficient times subscript, so 2 times 2 means that I must have started with 4 atoms of oxygen. So 1, 1, 4, 4, 4, 4. This is a balanced chemical equation. So this is how the equation happens. I have 1 molecule of CH4 reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. Let me erase all my work. Go my way. Okay. And so the slideshow clicks us through the same process here. So there's my tally. Oh, that was just a tally. It didn't go through the process. Okay. So some helpful hints as you're working through balancing chemical equations. Again, this is something that you're going to be asked to do, and the only way to get good at them is practice, practice, practice. So helpful hints here. If an element occurs in only 1 compound on both sides of the equation, balance that first. So here, hydrogen was in 1 compound as a reactant, hydrogen was in 1 compound as a product, and that's what we balanced first. Oxygen was a little bit more difficult because it was in 2 places, right? So that's why I didn't start with that one. So 1 and 1, that's a good place to start. If an element occurs as a free element on either side of the equation, balance that last. So again, back to our example. Here we see oxygen was a standalone as a reactant. That was really, really easy to manipulate at the end. So I could put a coefficient in front of oxygen, and that only changed oxygen. So that's always best to save for last because it's the easiest to manipulate at the end there. Always go back and double check your equantities, making sure that they're balanced on both sides. As you guys get more proficient at this, you're going to be moving through them faster, but you would be surprised how many things get missed. So it's always good to just go back and double check before you click submit for your answer. And then never, 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 ever, ever change the subscripts. We only can change coefficients. If you change a subscript, you've completely changed the identity of that molecule. And now it no longer is the same chemical reaction. It's something completely different. So that ends our discussion on chemical reactions or equations. Again, please get into this. Please practice it. This is one of those things where you can Google balancing chemical equations and get more practice worksheets with answer keys than you have time to do. The next video that I'm going to post is going to be walking us through how to math with these compounds. I hope you guys found this helpful.